It is my pleasure to introduce Professor Zhiqiang Gao here to our ISL Colloquium. Professor Gao received his PhD degree in electrical engineering from University of Notre Dame in 1990 and has taught in the Cleveland State University ever since. Professor Gao has had intensive collaborations with engineers in NASA and industry and have helped them solve lots of real-world control problems. And as one of the main developers of the new idea, but with a long history, called active disturbance rejection, Professor Gao has matured this conceptual idea into a real engineering system and has made lots of achievements in industry control. Just to name a few, you can see that the new idea, new technology has been commercialized in North America by a startup and financed in part by US venture partners, and also it has saved Parker Hannifin plant over 50% of energy across the 10 extrusion lines. Also, it has achieved 200% to 400% performance improvements in superconducting radio frequency cavities of modern linear particle accelerators at the National Superconducting Cyclotron Lab. And now it is hardwired into the DSP chips by Texas Instruments using under licensing agreement. So I'm pretty sure that in today's talk, Professor Gao is going to present us a fascinating history of this technology, and we will foresee together the promising future of this technology. Now let me give you Professor Gao.
Thank you, Zhiqiang. Thank you, Bobby, for making this possible. It's my great pleasure to come here and speak to you all. And my talk today is about an idea. About an idea that's been around for many years. And an idea that's reborn, an idea that almost died. Right? So it's more or less a story. So my talk will start with a historical perspective of cybernetics. And I'll concentrate on the great inventions in the system, and I'll try to reveal the attempt for conceptualization of these great inventions, and that will lead us naturally to active disturbance rejection. And it's no longer just a concept; it's a concept that's been put in practice. And I will talk about three particular industrial practice in extrusion, in motion control, and in superconducting cavity control. And I will conclude my talk with some remarks. First, let's review three greatest inventions, in my opinion, in history of control. We start with James Watt's flyable governor in 1780s. And this is an invention that's made the Industrial Revolution possible, as we all know. And as we will see just a bit later, there were many attempts on conceptualizing this invention. And the second invention, second great invention is the PID, Proportional Integral Derivative Control. And this was the first put together by Elmer Sperry in the attempt to automatically control ships and airplanes. And the first conceptualization was provided by Norm Minowski about 10 years later. Yeah. And the third invention is Harold Black's negative feedback amplifier. And that was in 1927. And we all know that it took him 10 years to get patented and to get the invention approved by U.S. Patent Office, and we'll see why that's the case. So in terms of conceptualization, it started with Clerk Maxwell in 1868. In 1868, he wrote the first paper in control on governors, and he was a pioneer. He found that the control system or dynamic system can be understood through differential equations. And he pioneered that approach. And I mentioned Minkowski in 1922, and he gave the PID formulation and stability conditions. But the greatest work happens in 1930s when Bode and Nyquist conceptualized hydroblast feedback amplifier invention, and that I think was what finally get him over the hump in terms of getting the invention proved. And then we come to 1948 with Nobel winner. He wrote a book on cybernetics, and that's that provided the foundation or the beginning of modern control theory. So this is a brief, very brief list of the effort to conceptualize the inventions. And it was Nobel winner in 1948 who came to this great understanding that control and communication or information theory are inseparable. And he, through the Second World War, in the effort of designing anti-aircraft artillery, and he found the universal concept of negative feedback, and that's the bedrock of his book on cybernetics. But in establishing cybernetics, he reached back to Maxwell, like we just said, the 1868 paper, and that was the he explained how he came up with this name, cybernetics. It's from the Greek word steerman. So from very beginning, you see the concept of control is very much the center of cybernetics. A well-known control historian, Otto Meyer, in 1971, actually wrote a paper on Maxwell's paper, on Maxwell conceptualization. He pointed out that Maxwell is a great scientist, but his work didn't really make an impact on industrial control. And he gave a list of reasons. And so from very beginning, you see there's a gap between the conceptualization and the invention themselves. Okay? So we come to this realization that it's human nature that we invent, and then we conceptualize. Okay? And we can see it happen repeatedly in the history of cybernetics. We compare the Watts steam engine with Maxwell's paper, Sperry's PID with Minkowski's paper, Black's amplifier with Bode and Nyquist, and in Second World War, anti-aircraft artillery, where the communication engineer and control engineer come together in the war effort, and that leads to Wiener's conceptualization in 1948. And this is a pattern in history that we cannot ignore. But once the modern control theory is established from 1960s to the present time, and we have seen this divergence between theory and practice. And to this point, we haven't seen a much large-scale application of the modern control theory in industry yet. We're looking at the PID technology which has dominated the industrial control for close to 100 years. So this is a very curious fact. And the modern control theory itself is shaped up more or less as applied mathematics. And in mathematics, we have a renowned mathematician, John von Neumann, who warned us in 1947, this is the year before Wiener's book, that you have to be aware that there's a grave danger in this kind of effort, that when you are taking a theoretical science away from its empirical source, and you are not careful with with how your how this branch of science developed. They could get away from the empirical beginning. And he warned us in this book or in this paper, you know. And then in 1970, when Otto Meyer wrote his book on history of control called The Origin of Feedback Control, and this is the first sentence in the book. He says that this field is essentially based on a single idea. A single idea of feedback. If the entire field is based on one single idea, right? Is that something that to be concerned with? Right? And could we say that we may be led to pass on a theory rich and idea poor? Should they have more ideas? Right? And let's see how is feedback studied. Right? Pretty much follow the follow Kirk Maxwell's lead that we model, we analyze, and we optimize. And we have accomplished quite a lot in that paradigm, from Maxwell paper all the way to the present modern control theory. But there are different voices, including Professor Vigil here. From 1971, his first paper on adaptive inverse control to 2008, his book on adaptive inverse control. And he spent close to 40 years on this idea. This idea that's not a single idea of control theory. And also, I include Professor Yu Ho from Harvard University. In 1982, he wrote a paper. He wrote an editorial in IEEE Transactions on automatic control. And he said, is this just application of theory, or is this a discipline of can be viewed as experimental science? Right? And in 2010, I think it's around 2010, and he raised the question: do we still have vitality in this field? And that's leads us to Professor Zhiqiang Han. He wrote first paper on active disturbance rejection control in 1989, and his last paper in 2009. He spent 20 years in his career focusing on this one idea called active disturbance rejection control, which we'll get into in more details. But I first want to pay tribute to Professor Vigil and his work on adaptive inverse control. Now, everyone was concentrating on feedback control. How do we design the feedback controller to make the output follow the input? Right? And he was one of the few scholars who has this keen insight. If you rely everything on feedback that put a lot of pressure, put a lot of burden on feedback that require you, for example, high bandwidth controller that's could cause stability problems, and also could cause noise issues in the feedback system. And so he constructed a different idea. He said, well, why don't we use the plant model? If we have model, why don't we invert this model and use the inverse as controller? Now, inverse may not be precise. So let's use a signal processing approach and make the parameter of controller adaptive. So you primarily you have a feed-forward control, but with feedback to take care of the uncertainty. And this is the idea he worked on for like close to 40 years, and in the attempt to find a simple, robust, and precise controller, right? And this is true to Norbert Wiener's spirit. In terms of, I'm honored to have the presence of Professor Vigil. I was just talking about your work. You were, and I think he was one of the scholars who stayed true to the conviction that control and signal processing, control information cannot be separated. And recently, there's a kind of reflection by the control community. Professor Carl Ostrom gave a plenary talk at last year's ACC, where he went through the history of control, and he advised us that we should not forget the foundation, because the tower will tumble. And he recognized that we are at a critical point in the development of control theory in this discipline, and he strongly suggests that we go back to foundation to see what's there, to make sure our foundation is solid, and that prompted us to ask, what is our foundation? Do we have a solid foundation? And this brings us to the ebook that's published online by IEEE Control System Society. And in the book, and I'm not going to read the whole thing to you, we're talking about the reinventing itself. We're talking about justifies our investment. Because at this juncture, it's hard for the control series to get funding. It's hard to justify because the theory has been under development for so many decades. Right? Why is this not the case where it's made a major impact in engineering practice? What is the issue? A single PID is still dominant in industry, right? And we're still in this mode of model and optimize. And even though we have some success in applying, in some cases, the modern control theory, but by and large, this is the mentioned in the book, that obtaining a good model is a challenge, right? Among other things. Right? So with that, let's look at a brief history of some other ideas. And that's a long history, right? And we're going to look at the south-pointing chariot. This is you mentioned in the history of China, going back thousands of years. And we're going to look at the Poncelet's isochronous governor, Soviet Union invariance principle, active disturbance region, and a bunch of others. But there's underlying conviction behind all this, that the problem control is a problem of disturbance and information. So we'll see that come out in each case. In south-pointing chariot, this goes back to the very beginning of Chinese culture. This was attributed to Emperor Huangdi, although there was no hidden. This is like a 2700 BC. There was no written record back then. The first written record goes back to 200 CE, and this is in the era of 3 warring states. And the record is this: you build a chariot, and you have a pointing finger on top of it. Right? And what you want to do is to make sure that this pointing finger points in the same direction. Doesn't matter how the chariot turns. So the army knows the direction, or the direction home. Right? And they built it. They built it, but there was a controversy in the history of China that people said, is this just a legend, or is it something real? So by the time of 200 CE, there was a debate in front of the one emperor. So Ma Jun was one of the people who said, actually, this is true. It happened, there was something like this. And they said, I'm going to show you by building it. So actually we built one. Right? And the idea is quite simple. You want this pointing figure to point to the same direction it started with. And you have, that's your reference direction. But how do you keep it there? Well, you devise a differential gear system where you detect the turning of the chariot. And then you rotate the pointing figure in the opposite direction. Okay? And that's negative feedback. And it works. If you search for at YouTube, you'll find many people have made it work using Lego. So there's the detailed account of this in the book Science and Civilization in China by Joseph Needham. And that's led us to the second crucial figure, Jean-Victor Poncelet, a Frenchman. Mathematician, and he wrote a book on projectile geometry. He was a soldier, imprisoned in Moscow, and wrote his book, best work in the prison. This is a legend. But in 1829, he wrote a book on industrial mechanics, and in that book, he drew a figure. He studied steam engine, like many other people. But he was one who recognized it's the lag in the flywheel that make the steam engine oscillate. So he was one of few people who recognized the true nature of feedback control and what make it singing. Right? And he was not just a pure scientist like Maxwell. He was an engineer. He said, "Let me show you how to fix it." He said, "I'm going to connect a mirroring device on the engine shaft where I detect the disturbance. And I'm going to use that information to change the valve directly before the engine speed slows down or speed up." And the Russian scholar attributed the name invariance principle to Poncelet. And that's leads to the Russian scholar. About 100 years later, more than 100 years later, in 1939, and this Russian scholar wrote a PhD dissertation on the invariance principle. Nobody understood it. And he didn't get his PhD, but he got an appointment as a professor because he was so brilliant. And in 1939, he wrote a shortened, more easy to understand paper. This time, everybody understood. And this time, he got into trouble. Because the invariance principle is perceived in conflict with the Soviet ideology. At that time, the ideology of revolution. Everything has to change in the revolution. Nothing stayed the same. So he was labeled counter-revolution. His paper were burned. He was driven out of the Soviet Academy of Sciences. I visited the Moscow, the Soviet Academy of Sciences in 2010, and I still talk to a few students of his students. So anyway, he coined he gave the name principle of the invariance to Poncelet, but he didn't go all the way because of the circumstances. The person who went further was Boris Petrov. He was a rocket scientist. He put it to use. He coined the term dual channel control system, where follow the lead of Poncelet, he measured disturbance. And this is the second channel. This is a regular feedback channel. Second channel, he measured disturbance and result. And this was very successful. And this for during the 50s and early 60s, it was red hot in Soviet Union. But then they died down then the modern control theory took over. But before it died down, another key person came into contact with it, and that's Professor Zhiqiang, and his daughter just came in. And he was a student in Moscow in the 1960s, and he studied it. He studied with punctuality. He was doing optimization left and right, but he was exposed to this idea. He didn't do anything with it. He came back to Beijing in the middle of Cultural Revolution. He didn't have any chance to do anything with it until after the Cultural Revolution in 1990s. He started to come back to this idea, and that's where active disturbance rejection was conceived. And in his book, in his paper, he paid tribute to the Soviet scholars, to his roots. And he and my father worked in the same institute, and we came into contact in 1990s. And I took this idea to U.S., to Cleveland State, and we worked on it for close to 20 years. And then we handed off to David, to U.S. venture partners to commercialize this idea. And so that's basically the nutshell of this story. So from Moscow to Beijing to Cleveland. So let's talk about what is active disturbance rejection. And start with the conviction as a foundational problem for coordinate control is disturbance rejection. It's not poor placement, it's not linearization, it's how well you reject disturbance. This is for Poncelet. He was the first one to recognize the importance of disturbance rejection. And this was inherited by Shipanov. This was inherited by Professor Zhiqiang. And the objective control is to hold your output in mind, despite of all these disturbance uncertainties. And disturbance here is in a more general sense, not just external disturbance, but also internal variation with point dynamic uncertainties. Right? And the key is how to extract the disturbance information. The information is there, it's hidden. This is where information and control come together. They stay on the same page. No winner was right. They should never be separated. The control problem at the bottom line is information problem. Right? And how to get it out? Signal processing, state estimation. So we turn a modeling problem, we turn a problem of mathematics into a problem of signal processing. So about the disturbance information, what kind of information do we need? How do we find it? After we find it, how do we use it? These are the basic questions of active disturbance rejection control. There are plenty of seeds you can set. Now, I'm going to put it in the, this is for practicing engineer to understand. Right? They start with PID. And there's internal dynamics, external disturbances. Just a single PID controller is inadequate to handle. So what we're saying is we can give you some help. So the input and output data, so a state observer, we call it extended state observer, I'll tell you why. We can extract the disturbance information or the information about uncertainty in real time. And the controller now has two signals to work with inside the one. And so any improvement we obtain is because we are using more information, because our controller has more information than before. Right? And this is the part we call active. It is the disturbance and unknown dynamic that cause output to to vary. Right? We're saying that if we can obtain that information before the output varies, then we're ahead. Right? So it's like a dual case of Professor Rizhou's approach. Professor Rizhou's approach is on the controller side, that if output varies, we're going to make adjustment to the controller parameters using signal processing approach. Okay? We're doing it in a similar manner, but instead of working on the controller, we're saying, let's make a design controller for an ideal plant. And if the plant deviates from the ideal plant, then we make a correction based on this information. So we're forcing the plant to behave in a certain way, instead of making adjustment in the controller to accommodate whatever changes in the plant. So the ideas are parallel. We all recognize the importance of not relying on a single feedback alone. We all recognize this field may not be based on single idea. But we go about doing this in a different way. And this is how I explain this to a lot of practicing engineers. Now, if you look at it, in industry, we have this empirical paradigm, where it's, we design and tune controller empirically. The controller reacts to the output change, but it's practical. The PID controller is used widely. It still dominates. And then we, on the other side, we have modern control paradigm, where it's model-based, where it's rigorous, where controller is optimized. Right? But here you need a transparency. You need a lot of information. So we could say that industry paradigm may be more like a black box approach, and the modern control paradigm is more like a white box approach. We need something in the middle. But we know something, but we don't know everything. A lot of uncertainty in there, but we know there's a basic structure in the plant. Like in the motion plant, we know the Newton's law. We may not know the friction, we may not know the load, but we know that our input is proportional to the acceleration. We're producing a motor torque, and that motor torque will change the acceleration. So that's it. That's what basically we know. Everything else, we treat it as a signal. We use the signal processing approach to see if we can extract this signal, and if we can extract it, then we can compensate for it before the output is changed in a significant way. So here we're dealing with this at the acceleration level. If we this is a 180 degree ahead of position, ahead of the output. So that's why we're more active. Let's use this motion control example that's everywhere in industry, in all manufacturing plant. The acceleration is function of all this, but this function may not be known. In the black box approach, you do not care what it is. You use a control law called PID in this form, and you tune 3 parameters, you make it work. That's how they deal with the uncertainties in industry, by and large. In the white box approach, you model it. You find the mathematical expression of this, and you find the mathematical expression of what you want, and you use control law to get rid of what you don't want, add what you want, and that's the basis. That's the idea behind pole placement, feedback, linearization, and all that. So what do we do here? Well, we come in the middle. We're saying, hey, this is the plant we're dealing with. Right? This is the ideal plant without all this. We design a controller for this. Right? And if somehow we can estimate this total disturbance, we can reduce the plant to this form, then our controller for this ideal form would work. Right? So that's the basic idea of active disturbance rejection. So if we can estimate F, and we can, in real time, and we compensate for it, we reduce the messy, nonlinear, time-varying, uncertain plant to something more ideal. So the key here is the estimation. So we reduce the problem of uncertainty, the problem of signal process, the problem of information. And how do we estimate it? Well, start from this, we're using the concept of state observer in motion control theory. So we're actually taking a part of motion control theory and apply it here. Okay? But this is how we apply it. But this is a second order system. Right? If you turn it into a state space, you will have two states. But here we define this unknown quantity, the third state. And we extend state information. That's where the extended state observer, where the ESO name comes from. Right? So this is the extended state formulation. And we build a Lundberg observer, or we build a nonlinear observer, whatever observer you can think of. It's in this form. And if the observer works, the third state will converge to F, or at least get close to F. And that gives us the information. That's the key piece of information PID doesn't have before. If we have this information, we can come back to this, substitute, put it here, and we can reduce the plant to an ideal form. Right? And this idea can be extended to a MIMO nonlinear time varying plant. Right? And this is more general form, but I'm sure you can find it in papers, and so I don't go into the details here. Right? So the train of thought is this. We start with cascade integral form, it's ideal form, the design controller for it. Right? Then we treat anything different from the ideal form, we treat as a disturbance, estimated, cancel it out. Right? Does it work? Does it work?
This video compares the performance of PID to a novel active disturbance rejection control under conditions of 8-fold increase in system loading. Both control the position of a wheel after one revolution. The first example as tuned for the nominal load of 4 small weights, and a second example for a load 8 times the nominal inertia. The controllers were not retuned for the increased load, and the active disturbance rejection control demonstrates its much wider tolerance to changes in systems dynamics.
And that's the PID with the additional weight. And same condition for EBRC. And this was done in 1997. It took us quite a few years to simplify it so that it can be easily implemented in the industrial plant. And this was done in 2010 at the Parker Hannifin plant. It's an extrusion plant, and it has immediate impact of 58% on average energy saving. And that number is something that people have a hard time to believe. So let me explain a little bit about this process. This is extrusion process. You add the plastic raw material in here. Let anybody play tennis. The string come out of this system, right? And it is crucial in this in barrel to control the temperature. They're divided into several zones, and also in a die, there's several temperature zones. And there are a lot of disturbances in this process, a lot of uncertainties. You're controlling temperature, you're controlling pressure, and there's a lot of variables: screw speed, temperature of the material coming in, and you are trying to control to keep output the product characteristic constant. And this problem, this multi-zone temperature control in industry, there's no good solution. You know, I once met an engineer who spent 6 months modeling this. This is the R&D, but it's impossible to do it on a factory floor. So every year they hire somebody to come in to tune the PID controller for them. And our approach here is we're going to, for 5 temperature zone, we're going to treat it 5 independent loops. And we'll use five ADRCs. And we're going to treat the coupling among different zones as disturbance. And this is the PID performance, where you see the fluctuation of the temperature going up and down. And you see the heating and the cooling come in and out. And this is just, people realize it's not perfect, but unless you spend 6 months, they spend $500,000 to model it, there's no cheap solution. So they do what they can. And this factory is supposed to be a world-class factory. And we had only a week to put in our code. Right? But once we put it in, look at this. The temperature fluctuation, animation. The temperature fluctuation become much smaller. All the fans are turned off. Only 3 heaters remain active. The two other heaters are turned off. So that's why you see such a big jump, big change in energy consumption. And this is the engineer working in the plant, telling us that only a week, and what happens afterwards. Once we switch the controller to ADRC, they never went back, and there was no maintenance. It's still operating. And more information can be found at this Ohio Polymer website. So that's the first example. Second example is ADRC in motion control. And this is again a third-party industrial verification. And in motion control, we are looking for 3 things: accuracy. In accuracy, we see 81% reduction in position error. In energy saving, we see 41% reduction. And in wear and tear, we see 71% reduction. Again, this is data obtained by a third party, and it's this kind of data that got us in agreement with Texas Instrument. And they signed a licensing agreement with Landstream, with the CSO spin-off, to commercialize this technology. The third example is in high energy physics. And this technology is making impact on science, on high energy physics, on particle accelerators. And this is probably the largest or second largest in the country. National Superconducting Cyclotron Lab at Michigan State. They've been working on the problem of vibration, the problem of what they call the microphonics. For many years, they reached an impasse. They don't know what to do, short of changing the structure. That costs a lot of money. So the chief engineer at the lab Googled disturbance rejection and found us. Very accidental. And we went in and we installed the new control algorithm. And we installed it on several superconducting cavities. I will not go into details of this high energy physics like. And the disturbances in this in superconducting cavity come from many sources. It used to be the case where you study each one separately and you try to come up with a solution. And all of them through different medium will affect the cavity. We installed we implemented the ADRC in their FPGA, and in simulation, this is interesting. In simulation, we only see 2 times improvement, that's 200%. But in hardware test, we see 400%. And it's been running since January 2011, over 2 years now. And there's some more curves. between PID and ADRC. And recently, they're upgrading their control systems on beyond superconducting cavities. And these are papers documenting the discovery. Right? And there's some equations that I just did here. If you're interested, you can see how the problem of vibration gets formulated as disturbance rejection. It's not intuitive. It takes a good understanding of the concept of ADRC and also good understanding of actual physical properties of the system. And together, you come up with a solution. And you come up with formulation of this. Once you put the formulation into this form, then you can use the extended state observer to estimate F, cancel it out, and that's how we get rid of the vibration. In this case, we have double loops. One control the phase, one control the amplitude. So, let me put the active disturbance rejection in a nutshell. What problem are we dealing with? We're dealing with internal and external disturbance. And we normally call it disturbance rejection, but that word becomes a little weak. So what we really want to achieve is decoupling. We want, ideally, the disturbance has no impact on the output. That's our goal. And that's the conviction we inherit from Poncelet, from Zhiqiang, from Han. And we want to do it in an active way. We don't want wait until the output deviates. We want to do it as soon as we capture the information, we act on it. So this is more of an active as opposed to passive disturbance, disturbance rejection. And this is because this is possible because the disturbance information is there all the time. We just didn't know. We found a way to get it. Right? And the way we estimate disturbance is not unique. There are other methods, right? But they're all isolated. They're all for a particular problem. They devise a particular way of doing it. But what we are saying here is active disturbance rejection is a universal concept. All of that techniques can be brought under this one umbrella. And the method of the key method is to estimate total effect of the disturbance. And that's where the extended state observer comes in. And the solution we propose is parameterized ADRC. Now, remember ADRC was a success in 1997. But it was so hard to use. It took my PhD student a couple years to make it work. Obviously, that's not an industrial solution yet. To go from there to industrial solution, you must make it easy to use, easy to tune, simple to implement. That is not something that we in university do very well. So it took us 6 years, from 1997 to 2003. We found a way to make that transition. And that in 2003, it became a technology. It took us another 7 years to put it in the factory, because you have a lot of convincing to do. So at the end, it started with some papers, and then patents. We applied 3 or 4 patents. We have a clean state spin-off financed by U.S. venture partners. Now we're on the verge of licensing it. We already licensed to Texas Instruments. We're on the verge of making a massive industrial introduction. That's where we are. In terms of ADRC technology, we can say it's can be seen as a few line of code. In the industrial control like a PLC, there's thousands of lines of code, but crucial to control functions is a few line of code. And we take out PID, replace it with ADRC. So coding-wise, very simple. No hardware change. And this can be done across platforms, from microcontrollers to DSP chips to FPGA, DCS, PLC, you name it. And we have validated this in the manufacturing environment. There are some tests we cannot disclose because it's under NDA. But we took a miniature manufacturing process, and we validated it. And we show people how much money it will save on one machine. And we've done this motion, in temperature, in web tension, in aerospace, and in aeronautics. We've done it in jet engine control, power management, and I mentioned the high energy physics. But it's really, we don't see a hard bound where this control technology cannot be applied. It's in everywhere you apply control, closed control, you have this need to be anticipated, to not wait around, to not wait around, and to act quickly. So in conclusion, we have seen a long, fascinating story. And this is the idea that's been there all along. We just didn't notice it for many, many years. And we become sort of single-minded, dominated by a single idea. But as we saw in Professor Guizhou's work, in Professor Han's work, there are other ideas. There are other alternatives. Right? But maybe it's about time for us to look at these alternatives, to look at our foundational ideas, to look at the foundation of automatic control, to see where we are, to see where we should be. And this field could use a big idea like this. We should recognize the importance of disturbance rejection in all control systems. And that's the reason we believe to have a control system in the first place. And also, let me make one last point. Is in our research, we try to make a difference, not just a point in a paper or in a discussion. There are plenty of people do that in academia. We don't have to be just one more group. We, at Cleveland State, we want our research to make a difference. And we wanted that for a long time. And we are starting to see the effects after so many years of effort. Thank you very much.
How do you see this in comparison with fuzzy control?
That's a very good question. When I first started at Cleveland State, my first instinct was fuzzy logic. Because there's so much uncertainty and there's so much heuristics on the part of control engineers. Why don't we program controller to take advantage of those experiences? We have like 3-4 master theses done in fuzzy logic control. And, most of them are implemented in hardware, either in our lab or at the factory. It works very well. It's for one particular system with a student working, taking about a year, we can make system work wonders. But at the end of the day, I recognize that it's not going to be a massively applicable. But every system has to be engineered differently.
But
you cannot easily scale it.
But you can automatically generate fuzzy control rules from from the wavelet of the signal.
Yes, we studied the wavelet too.
Yes.
Okay, so we're looking for an angle to see how the best way to handle the uncertainty.
Yes.
And we believe to go off differential equation approach completely to make the controller rule-based, that's a huge jump. That's a huge jump. And we already accumulated so much expertise, understanding on the control theoretic side. We're trying to find the best combination of what we learned in the past, okay? What problem presents, what the challenge presents us, and most importantly, the industrial solution. Something has to be simple, something has to be easily tuned, something is very robust, has very wide range of applications. So fuzzy controller can work very well on some problems, but as a general industrial solution, it's going to take a while to get there.
I thought, but here, forgive my ignorance,
Yeah.
I thought you still have to come up with a model
No.
to start with.
See,
Is that what I saw on one of your slides?
not detailed model.
Oh,
Yeah, this F
yes,
business.
yes.
If you identify the system using the modeling approach, you find a mathematical expression of it.
Yes.
Right? And that's the basis of modern control theory, is you must have a mathematical expression. In this approach, we're saying we don't need mathematical expression. We need a signal expression. We need to estimate that signal in real time. Right? That's how we simplify the controller greatly. And that's make it the biggest difference. So you are right. Fuzzy logic is an alternative, just like ADRC is an alternative to model-based design. But there are some limitations that I believe prevent fuzzy logic to be a potential replacement of PID.
So yeah, I was gonna say along those lines, like plant estimation, and I also don't know. I'm saying too much about this area. I don't know what you're talking about, but it seems like you fit a parametric. You basically assume a parametric expression, like a linear plant model, and then you kind of empirically do state estimation, and you find like a maximum likelihood fit to the input-output data for that parametric form online, and then you base that on your controller and do kind of feedback linearization based on that active model. And I'm probably butchering a lot of this, but that's what it seemed like. So it's still, you still need some plant model, and it needs to be parametric, and then you'll basically do an active online estimation of that, assume that that's true, and then kind of hope that all the parametric variation, if the plant parameters change, you still have kind of enough wiggle room to do kind of active online estimation in that parametric framework for your plant model. And that the strength of this is that you can adapt to changes in your plant model because you're simultaneously estimating the model and the disturbance jointly as just a general disturbance. And then you're fitting it to that. So that instead it's basically, we've gone from fixed model plus disturbance, which is wrong, to just giving us a lot more degrees of freedom to say what we really care about is the output disturbance. But is this a fair interpretation? I'm just asking because
well,
kind of online estimation and control mixed in with that.
There's a lot of truth in what you said. But the names, sometimes we get caught up in language.
Sure.
The parametric model means, to me, that you already have the mathematical expression. It's just the parameters are not certain, right?
Yeah.
In that sense, this method doesn't require that.
But then, I mean, F is not just, it's not just a signal. I
Well,
saw an equation there where it was in terms of variables, and I think that's where our confusion is, that
Yeah.
it's not just a non-parametric model or a data-driven model
Right.
for F.
The F could be a nonlinear.
Yeah, sure.
Could be uncertain. Could be anything.
No,
right?
but then F
Right.
hat is.
F hat is a real-time estimation of it.
Yes.
Not the model of it.
Okay, sorry.
Real-time estimation.
So, but your real-time I mean, to some degree, like what the real F is completely irrelevant to this because it's what generates your signal. But what you're basing your
Exactly.
control actions off of is F hat.
The signal.
And yeah, but it's a parameter fit to that in some way, or
We are not assuming that we know the structure of that.
okay.
We're not assuming that we know the even any parameters.
Mhm. Yeah, no, I understand, but
So if I may, maybe the model we're using is y double dot equal u.
yeah,
That's ideal integral plan. That's a pure
yeah,
integral plan. And we're treating anything
anything.
away from that
Mhm.
as the f
Okay.
estimated cancel out.
It actually doesn't seem completely true, because for oscillations, you seem to take
Yeah.
a more detailed model of the plant. You include omega squared, right? As x double dot plus omega squared.
Well, in the
as,
higher energy, right.
Yeah.
Well, in actually, no, that's a fair question. You're saying in that particular application, you already know the structure. You already have the structure.
Yeah, so
Right.
you take dominant structure, and normally you assume that it is a
Right.
bunch of integrators plus this
Right.
plus
Right.
unknown part.
Right.
But for oscillations, you say it's x double dot plus omega squared x plus
Right.
the
Right.
rest of dynamics.
Right. So the omega square could be unknown. In that case, you say that's a parametric model.
But that's not what we did.
No.
for binary.
No, we're treating the whole thing as unknown, and we're estimating it in real time.
Or you're estimating omega as well?
Not omega, f. No.
The rest of it?
Yeah.
Okay, understood.
Yeah.
So, do we have any other dominant dynamics cases? So it's multiple integrators and oscillator. Is that it? Or do you use some knowledge of dominant dynamics?
That's an excellent question. Sometimes you do know the dynamic structure. Part of that is already known. Why do you not take advantage of it?
I understand you can't.
That can be taken into consideration in the structure of the state estimator.
Mhm.
If you know the dynamics, you can put it in.
So
I don't have time to go over the details of that, but information like that can be incorporated into the observer so that observer doesn't require such a high bandwidth. So if you assume you know nothing, then all of f has to be estimated by the observer. But if you know part of f, then observer only need to estimate what's unknown part. And that will reducing the bandwidth is holy grail in industry. You want to use as lowest bandwidth as possible. And this will solve your noise problem. This will solve your stability problem. But this is not emphasized in academia. But taking advantage of our knowledge of the plant help us to reduce the bandwidth of the observer. And that's a product. In one case, in MEMS, we apply this in MEMS gyroscope by applying the omega squared y and the damping term. By incorporating that into the observer, we were able to reduce the bandwidth by 3 magnitude. So that worked out very well. So at the end, here I emphasize in a brief introduction that this method can be completely independent of knowledge of F. But in actuality, if you know part of F, which is the case in most cases, you can incorporate that into the observer and make your controller more efficient.
Estimate the rest. Yeah.
Right.
Yeah. Which is fine. Yeah.
So I think you got the gist.
Well,
It's
no,
just sometimes we get the terminology in conflict.
I'll take it offline. I still have some questions about what you mean by state estimation. But
Okay.
take it offline.
Yes.
Are you familiar with anticipatory computing? University of Ghent, Belgium, that work on anticipatory computing. I see this as an example of anticipatory computing and anticipatory physics. Does that make any sense?
Anticipation is a big word.
Yeah.
Anticipation is a big word in control from the very beginning.
Yes.
In 1911, when Alma Sperry put together a mechanical PID, and what's big in his design is anticipatory behavior of his controller. When Norm Minovsky conceptualized that controller, he admitted at the end of his article, he said, my controller, this controller does not anticipate.
Correct, because it's a feedback.
Right.
Yes.
Right, so Minovsky realized that he was missing something.
Yes.
Elmer Sperry
Yes.
did it, but
I'm-
couldn't come up with mathematical description of it.
Yes, I'm trying to draw your attention to that. This is
Right.
an example, a solid example that works of
Right.
anticipatory controller and anticipatory computing. There is a theory out there, and it's there's a lot of body of work, lots of it in Europe though, in that field.
Thank you for pointing out.
The extended state estimator, state observer,
Mhm.
and the estimation process. There's some time series of some suite of state variables
Right.
there. Okay. And thinking about that, it sort of reminds me of the way there's a lot of linearization that gets done by, in effect, predistortion or precompensation,
Mhm.
where you say, oh, okay, I see what's going on here. My plant is drifting around. That my big power amplifier is heating up, or something's going on to change its transfer function. And there is to some degree a machine learning kind of process whereby it predicts, okay, that's already started. I know where that's going to go, or at least I can guess where it's going to go. So I'm going to modify. I'm going to predistort the input a little bit to see what happens, and then now I begin to form a model of the effect of that predistortion,
Mhm.
and so on. And although that's usually done in the field of RF, that's the way big cell phone towers manage their linearity and so on. But the point is, as far as I can tell, it's pretty much, homomorphic to what you're doing. It's just a different time regime, a different loop bandwidth, and so on. But it has the same character, right?
Exactly. You point out a very important fact. Mathematical biologist Robert Rosen says this: at the root of intelligence is anticipation.
Yes.
So you find anticipation everywhere. And sometimes we just didn't recognize the connection among different fields. So that's very true. And also, when we talk about plant transfer function drift, using time theory to correct it, and that's precisely what Professor Guizhou did, starting in 1971. You have a transfer function of plant, you invert it to control it, but the plant drifts. So what you do, you use adaptive algorithm to make real-time adjustment. So you follow the change in the So that's another type of intelligence. Even Professor Wiener emphasized in his books cybernetics about learning, machine learning. That's ideal. That's a goal that we've been all seeking. And Professor Han once said that the longer your controller runs, the better its performance should be. And that's a fun way to make it happen. What we present here is a building block, is a fundamental building block. And at this year's ACC, 2013 ACC, this is June 17th to 19th. There's a pre-conference workshop on June 15th and 16th on ADRC. And we have united 12 speakers from around the world to come and discuss with us about what has been done and what needs to be done. So we have an event at ADC this year. You're all welcome to join us, and we're going to discuss the frontiers of this technology. We're going to discuss where we go from it. And this is a very modest beginning, and we start to see the benefits, and we start to see industrial scale benefits. But there's a lot more to be accomplished, both on the industrial side and on the academic side. Thank you.